The shouting and paper-strewn chaos of the old trading floors has been replaced by silent, ruthless, algorithmic efficiency. Modern exchanges must process up to 1 billion orders a day, hitting peak loads of 215,000 queries per second. Our primary engineering battle lies in maintaining perfectly stable, sub-millisecond latency for every single transaction. All incoming instructional data from institutional clients will arrive via the Standardized Financial Information Exchange, or FIX protocol. The L3 order book serves as the core battleground, tracking the exact quantitative volume queued sequentially at specific price levels for both bids and asks. To prevent latency spikes that cost institutional clients millions, we must engineer a system that eliminates all unpredictable computational friction. The matching engine matches incoming bids to resting asks instantly, performing every operation in memory without ever scanning a database. Iterating through a standard array or list to cancel an order would blow our latency budget during periods of extreme market volatility. An O of 1 order book uses a doubly-linked list embedded within a hash map. New limit orders are placed at the tail in constant time. Orders are instantly extracted via direct hash map reference, ensuring consistent speed regardless of list length. Guaranteeing constant time O of 1 operations for every data manipulation is the only way to ensure deterministic execution speeds regardless of market load. A standard modern architecture would utilize load balancers, message queues, and sharded databases to handle this volume. However, the network hops and inter-process communication required for this design destroy a sub-millisecond latency budget. We will aggressively split our architecture, moving risk checks and wallet withholding entirely upfront via the order manager to keep the engine lean. To achieve microsecond stability, the entire critical trading path must be isolated onto a single, vertically scaled server. We utilize single-threaded application loops for the matching engine to avoid overhead. Pinning these threads to specific CPU cores eliminates context switching. The database is removed entirely, replaced by an mmap memory bus to share data directly between processes without disk I/O. This critical path functions as a zero IPC lock-free memory loop designed to outrun the network itself. Asynchronous network inputs create chaos. If orders arrive simultaneously from different brokers, the matching engine cannot determine a fair order on its own. The sequencer serves as the absolute single source of truth, intercepting all traffic directly in front of the matching engine. This creates an immutable event log, ensuring every order is strictly ordered. The matching engine then operates as a state machine, processing this sequentially stamped log to produce deterministic execution fills. Event sourcing mathematically guarantees fairness. By relying on a strict sequence, we ensure no client bypasses the queue, and every state change is perfectly auditable. While the matching engine remains isolated, clients require real-time candlestick charts and L3 order book data to navigate the market. The market data publisher utilizes lock-free ring buffers to continuously ingest execution fills without slowing down the critical path. The publisher transforms these raw execution fills into standardized market data like candlestick charts. We broadcast this data to institutional clients via multicast UDP to ensure simultaneous delivery to all participants. For co-located trading firms, the only remaining speed limit is the absolute speed of light traveling through a fiber optic cable. In high-frequency trading, information asymmetry is wildly profitable, making network-level fairness a strict regulatory and architectural requirement. Running an entire exchange on a single vertically scaled server creates a catastrophic risk. Hardware failure means immediate market collapse. Our strategy utilizes a hot-warm standby architecture, where the warm node silently mirrors the primary node's internal state. Because of our deterministic event sourcing, the warm node simply processes the exact same mmap event log to maintain perfect state parity. We use the Raft consensus algorithm to verify the state of the mmap event log across backup servers and trigger an instant failover if the primary node fails. This architecture guarantees zero data loss and second-level recovery times. Beyond hardware failure, we must also defend the perimeter against malicious external traffic. Network gateways enforce strict rate limiting and block lists to neutralize DDoS attacks before they ever reach the critical path. The final architecture is a perfectly deterministic, replayable, and lock-free state machine, where every single microsecond is carefully accounted for.